Welcome. This is a complete unit review of the Financial Applications unit covering compound interest and annuities. Specifically, we're going to look at compound interest, future value, and present value in those situations shown on the screen. This is a complete overview of the Financial Applications unit in grade 11 math, but it's helpful for all who want to learn about compound interest and annuities. This question says, Marissa has just won a contest. She must decide between two prize options. Collect a lump sum payment of $50,000, all one time, or receive $1,500 at the end of each quarter for 10 years. If she invests all her winnings in an investment that earns 6% per annum compounded quarterly, which is the better option after 10 years and by how much? So we're going to look at the first situation first, the lump sum of $50,000. And so she gets a present value of $50,000, and then she's going to invest that for 10 years quarterly. That means 4 times per year. We always take the number of times per year, and then we multiply that by the number of years. So 4 times 10, so the number of compounding periods is going to be 40. So she's going to get interest paid out 40 times on this $50,000 investment. The interest rate is 6% per annum compounded quarterly. So we write that as a decimal and divide it by 4. And what we do is we then make sure we divide the I by the same value that we multiply the N by, the number of years by. So we get I is 0.015, and we're trying to find the future amount. In 10 years' time, how much is it going to be worth? And the equation we use is that the future amount, A, is equal to the principal, P, times 1 plus I to the N. So P is $50,000, and then we sub the other numbers in. We get 1 plus 0.015 to the power of 40. And so effectively what we're going to do is we're going to multiply 50,000 times 1.015 40 times. That's what the power of 40 is doing. So that interest is accumulating 40 times throughout the investment. It's important to remember that we apply the exponent before we multiply it by 50,000. And so I've done that here. You don't have to show this step, but I've done that here just to show you how that works. And you should get a total number of $90,700.92. You've made $40,700.92 interest. That's quite significant over a period of 10 years. You've almost doubled your money. You started at $50,000 and you have over $40,000 now. Now let's look at the second situation. What if Marissa had received $1,500 at the end of each quarter? Those are regular payments that are made out to her, and she's going to put those into the investment as regular payments into the investment. The N value, the number of compounding periods, is 4 times 10, just like it was before, so 40. And the I value, same as before, again. Whatever you multiply the number of years by, you have to divide the I by. And so we get 0.015 for that. And we're trying to figure out what that future value is. You could call that an A again, but I call that FV for future value just to distinguish it between a one-time investment like we had on the left. So the equation we're going to use is the equation right there. Future value is the regular payment times 1 plus I to the N minus 1 all over I. So we go ahead and we sub those numbers in, $1,500 for the R value, and then 1 plus 0.015 to the power of 40. Then we have to subtract 1 before we multiply into that by 1,500. And then we divide that by 0.015. And so the future value is equal to, just taking the steps with this, we do what's in the square brackets first, and we should get a value of 0.8140, and then that goes on from there. And we then divide all that by 0.015. And so that gives me that the future value should be a value of $81,401.84. Now that's significantly less than we would have gotten with the initial situation, but let's have a look at what the differences are. The first difference is how much did she actually put in, or how much was she paid that she put into her account? Well, her regular payments were $1,500 and she was paid those 40 times. So she actually received $60,000 in this second case. You'd think that would amount to more, but she only gets $21,401.84. So the difference between $60,000 and $81,000, about $21,000, that's all the interest she's earned. Well, the reason for that is because she actually has gotten very little interest on those later payments, and the initial payments early on were very low. They were only $1,500 and then $3,000 total and then $4,500. And so that money that was paid earlier on didn't get much interest because there wasn't a lot of money initially in her account. So the first option is better. And what she's going to get is she's going to get quite a significant amount more by using that first option. She's going to get $90,700.92, subtract the $81,401.84. So she's going to end up with just about $9,300 more interest by choosing option 1. The power of compound interest with a big upfront payment is super powerful for you. But regardless, she's still getting a lot of interest by using the other option. But if she had the money up front, it would have been a better option. So Marissa should have chosen the lump sum payment of $50,000. If you have student debt, do you ever wonder how long it's going to take to pay it off and how much you're going to end up paying total? Here's a perfect example that shows you the average in Canada, what that would look like. It says this: Kyla must repay student loans that total $28,000. She can afford to make $340 monthly payments on her loan. The bank is charging an interest rate of 7.2% per annum compounded monthly. How long will it take her to pay off the student debt, and how much interest will she have paid? So let's get down to it. The equation that we need to use here is the present value equation, but the value that we want to start with is that present value. So we're starting with $28,000 and we're paying that off down to 0. So that's why we're not using the future value equation. The regular payments that Kyla is making is $340. And the interest rate, the I value that we use is we make that a decimal, we take that then and we divide it by the number of compounding periods per year. And because it's compounded monthly, there's 12 per year, so we divide it by 12. And so we're trying to figure out how long it's going to take to pay off. We're trying to find the n value, and it's worth noting as well that the n value corresponds with the compounding periods per year. So that's 12 payments per year, and then there's however many years it takes to pay off. So the n is the number of months that we have to divide by 12 at the end. So the equation we're going to use is this: PV equals R times 1 minus 1 plus I to the negative n all over I. And it's just good to have an idea of what this actually looks like in reality. We have some amount that we're starting off with, and then over time we're going to pay it off faster and faster because more of our payments go towards the principal and less towards the interest over time. It's going to look a shape something like that. So let's go ahead and rearrange this equation before putting the numbers in, just because it's a messy equation and just the variables make it a little shorter to rearrange. So we're going to multiply both sides by 1 over r, and that's going to give me I times PV over r equals 1 minus 1 plus I to the negative n, what was in the square brackets. We can get rid of the square brackets now because that's by itself on the right. If we subtract 1 from both sides, now we get I PV over r minus 1. And that's equal to negative 1 plus I to the negative n. We're getting closer to rearranging for negative n here. But before we do that, we have to multiply by negative 1 to make that positive. And then whatever you do to one side, you have to do to the other. And so we're going to multiply the negative 1 in, which is effectively going to make the 1 positive and the IPV over R negative. So we could write that in the opposite order as 1 minus IPV over R. And then we have 1 plus I to the negative n. Now, in order to solve this, the only way to do this is using some type of logarithm. And so we're just going to use a basic logarithm. And if we take the log of the left side, we have to do the same thing to the other side. And what that logarithm does, without knowing more about logarithms, is it effectively just brings the exponent out front. And so we can write the same thing on the left as I had on the line previously, but now on the right, this becomes negative n times log of 1 plus I. And that exponent now is gone from that. So now what I want to do is I want to divide by the log of 1 plus I to get just negative n on the right side. Whatever you do to the one side, you have to do to the other. And the logs don't actually cancel on the left side. And it's because it's very much like sine or cosine that operates on something. It's not like they're being multiplied and you can divide them out. So they operate on what follows. So it's very important you keep the log in both the numerator and denominator. The final step here is recognizing that there is a negative n left on the right. So we're going to multiply both sides by negative 1. And so we have the same thing we had above, but there's a negative on the left side, and on the right, the n is positive. And it's important to keep in mind that n is the number of months. We're going to get a large number. It doesn't mean it's going to take this many years to pay it off. It's the number of months. So let's go ahead and sub some numbers in and actually solve this now. So n is equal to negative log of 1 minus, the I value was 0.006. We're going to multiply that by the present value of $28,000. And we're dividing that by the regular payment of $340 that she's making. Then we're going to divide all of that by log of 1 plus I, 1 plus 0.006. So now we can go ahead and calculate what's after the logs. It's good to simplify that first just so we don't make mistakes. So if you do that, 1 minus the 0.006 times 28,000 over 340, you end up with approximately 0.50588. And then on the bottom, we can simplify that to 1.006. And if you then take the negative log of the numerator and divide by log of the denominator, we end up with almost 114, 113.916. And so you always have to get to that next payment to finish paying off the debt. And so we're going to say it's 114 months in order for her to pay this off. Now, I said that was the number of months. So if we divide that by 12, we end up getting 9 and 6/12, which gives me 9 years, 6 months. That's how long it's going to take her to pay off her debt. Now, $28,000, almost 10 years to pay it off. That's quite a significant time of someone's life. Well, how much interest did they pay? How much interest did Kyla pay here? Well, she paid $340 114 times. The last time might be a little bit less than $340 because we didn't quite get exactly 114, but it's around this number. So she pays $38,760 back, and she only borrowed $28,000. So that means she almost had $11,000 nearly in interest that she had to pay. So have a look back at the graph on the top right again, and you'll see that near the end the line is steeper, but towards the beginning of the time the line was less steep. And that's because at the end you're paying off more principal, you're paying it down faster, whereas at the beginning you're paying almost all of your payments towards interest. So it's really in your best interest, pun intended, to pay it off as fast as possible so this doesn't last longer and charge you more and more interest. In fact, 7.2% is not that big of an interest rate on a loan. Some people have credit card debt that could be 19 all the way up to 29%, and that interest rate could just swamp them if they don't get that paid very quickly. So it's very important you pay your debts down fast, but then you use this to your advantage by investing money over the long term to get interest working for you so that you can gain long term. For more on annuities, check out the video on the left. For a complete playlist of financial application videos, check out the playlist on the right. Thanks so much for watching. Please like and subscribe, and I hope that was helpful.